And my dear friends, I know you have been in this classroom for more than an hour, and it's likely that you're a little bit bored already. Thus, I will try to make a minimally boring presentation for you. My subject is face recognition by non-negative independent component analysis. The project I have done can be considered as a combination of three fields: image processing, pattern recognition, and subspace methods. So I hope that you're going to find something interesting in it. I will first introduce what is face recognition technology and talk a little bit on pertinent methods in literature and introduce the proposed algorithm non-negative ICA and show my experimental results, compare the different methods and submit to you the conclusion. What is face recognition technology? After the very recent Boston bombing incident, in Michigan University laboratories, pattern recognition and image processing laboratories, they identified the suspect with 100% accuracy. This shows actually the importance of face recognition in our lives in a very recent incident. However, face recognition technology is used in our daily lives too, as in smart doors, ID verification cases, and also even after very small robberies that happen in our city so much. The face recognition can be considered in two manners. One is face verification, which is a one-to-one match. Is this person this? Yes or no? And face identification, it's one-to-many matches. Who is this person? I will take the challenge a little bit bigger this time, and we're going to do face identification. Let's assume that we have a classifier that uses a database of images. We capture the camera image, and then you detect the face in the image, and then use this classifier to get the ID. So this is the main, very coarse face recognition model. However, we see that in human faces that the area is very smooth. The neighboring pixels have a lot of correlations, and it's pretty symmetric through the origin. So let's call this image space, and an image space is too big to run pixel-to-pixel verification methods. So what are we going to do? We're going to introduce a smaller space called face space. We're going to reduce the redundancy, separate characteristic features, and make the classes as invariant to changes as possible. Changes like illumination, or the girl can make a makeup, or mustache, beards, whatever. But how are we gonna do? The main point here is the challenge called feature extraction. The feature extraction leads us to the pertinent methods in the literature. The goal of feature extraction is extract the most important features in images and represent the image as combinations of features. The big size dimension image, it's represented with a smaller dimension of the features times the components. This is the main challenge. So now our classification model is a little bit changed to get the training images and extract their features and get the features and train the classifier with only these small size features, and get and when we have a testing image, we project the image on the subspace spanned by the features that we use, and get the components out of it, and then test in the classifier and get the result. the features can be in linear spaces or nonlinear spaces. The mostly used linear spaces are the features in face recognition. Probably the most the pattern recognition technology is as follows: probabilistic eigenspaces, Eigen-Faces and related techniques, linear discriminants, Bayesian methods, independent component analysis, and multilinear SVD. Also, nonlinear spaces can be seen as follows. I'm going to introduce you the heart of it, the most important one, the Eigen-Faces, which is basically PCA, and ICA that we mostly use in this class, and the proposed algorithm non-negative ICA. Eigen-Faces meaning also means one's own face utilizes the two-dimensional global grayscale images representing distinctive characters. PCA generally gets the most important features from multidimensional data, and we introduce ICA as feature extraction. We not only get the uncorrelated components, which are the principal components get achieved by PCA, we are going to introduce something new. They are going to be independent sources, and it's achieved by ICA. So we're going to state the face images as independent sources mixed with some random mixing matrix. But what is it going to bring to us? In a specific task like face recognition, the most important information may be hidden in higher order statistics, not just second order statistics. The second order statistics are used by PCA. An example would be phase and amplitude spectrums. Amplitude spectrums are captured by second order statistics. However, phase spectrum is hidden in higher order statistics. The phase spectrum is mostly applies to human perception. Let's show that with an example. Let's get this guy and this woman and extract their phase spectrum and amplitude spectrum. But take guy's phase spectrum here and amplitude spectrum here. Likewise, let's extract the woman's phase spectrum on the guy's amplitude spectrum and her amplitude spectrum on guy's phase spectrum, and combine them. What do we get? We get that we see the woman here. So the more information pertaining to human eye is hidden in phase spectrum. This example shows it to us very good. There are two main architectures of ICA image representation. The architecture 1 treats the images as random variables and the pixels as outcomes, where architecture 2 is the opposite, treats pixels as random variables and different images as outcomes of this independent experiment. If we try to look at what architectures suggest us, in architecture 2, which we generally use in this throughout this class, we concatenated the columns of the image, the pixels, and try to find the independent components out of the pixels, and the faces, the images are the random outcomes. So they are the columns and the rows are the pixels in our algorithm. Therefore, I use the architecture 2. So we're trying to find some undefined mixing matrix, and this columns of this mixing matrix will be the basis images. We're going to find the basis images. By ICA, we're going to get the learned filters. And now it's time to introduce the new algorithm, non-negative ICA. In real-life problems, the sources are generally non-negative. What does non-negative mean? The source is called non-negative if the probability of the source being 0 is 0. It's always non-negative. And it's well-grounded if it is bounded to some degree. And here is the life-saving theorem that if the vector S is non-negative and well-grounded, the independent unit variance sources and the Y is just the rotation of these independent sources. Y SI's are independent if and only if Y are non-negative. So the situation is the same as what we ended up with right after the whitening transformation with PCA, an arbitrary rotation of the source vector. If we look at the whitening matrix V, the whitened vector Z is basically the V times A and S. Therefore, since VA is itself orthogonal, the S can be stated as VA transpose Z. So as stated in the theorem, Y is a rotation, random rotation of S. Then the non-negative estimates are a rotation times VA transpose, which is already orthogonal, so the separation matrix will be orthogonal. So our goal is to find an orthogonal matrix W for which Y is non-negative. It's way simpler than we used in classic ICA. It's much easier than searching for non-Gaussianities or mutual information. So let's assume that our cost function for W, we're going to get the W here, is minimizing the distance between the non-negative estimates and the whitened space. And non-negativity here is done by only truncating the non-zero parts of the estimates. So our nonlinear function that we all the time used in classical ICA is just a truncation of the estimates. And if we include the orthogonality part here too, we get the cost function like this. When we take the gradient of it, we get the update algorithm like minimizing the distance between the estimates and the new incoming data and the non-zero estimates, and this part accounts for the orthogonality part. For the experimental results, I used the ORL's database, which has 40 subjects and 10 face images of each subject. Some examples of the faces in the database are as follows. So what did I do? I took the first 7 samples of everybody, every person, every subject of this experiment, and used it as a training, and used the remaining 3 samples of everybody as testing, and I used the classifier. So this is a 40 class problem. I use 3 different feature sets. The three feature sets that I introduced 2 minutes ago. First, Eigen-Faces, ICA, and non-negative ICA. Then I calculated the correct classification rate using different dimensions. But how does it work? First, let me introduce what did I do with the Eigen-Faces. Let's introduce our training and testing matrices. So as we always did, the training matrix is just a concatenation of the images. So it's a huge matrix of dimension m times n times 280, 7 images per person, and 40 people, so it's 280. And likewise the testing matrix is this. However, this m times n is a huge number, so we did some dimension reduction as in the whiting part. We calculated the training covariance matrix and found the eigendecomposition of it, and used the most important eigenvectors and projected the training matrix on the space. So this is the feature set. The projection is the feature set of Eigen-Faces training. Likewise, we projected testing images on the same subspace by Eigen-Faces. I say same, really the same, because I wasted a lot of time. I used the eigenvectors of the testing image, but no, this should be the same space. Classical ICA works with the whitening and dimension reduction at the same time. We calculate the whitening matrix with the eigenvalues, square root of the eigenvalues, and the most important eigenvectors, and projected the training and testing matrices onto the same subspace, same whitening subspace. This part is very important too. And ICA features are achieved by the classical fast ICA algorithm, and we also get the mixing matrix and demixing matrix. And we use this demixing matrix here to project the testing images on the subspace and get the ICA features testing. And with the non-negative ICA, starting with an initial random matrix or the identity demixing matrix W, I iterated this algorithm until it converges and got the W, and projected the training images on the subspace and separated the images, training images and testing images with the same demixing matrix, and get the non-negative ICA features for training and testing. The classification for the classification, I use the PR tools of MATLAB and use support vector machines. The datasets, which includes the labels here, is done with the dataset, and for the classification, I used the SVC command and gets the separating weight vectors, and use the same separating weight vectors to test the data set of testing and get the error with it. If I compare different results, I did the comparison under different dimensions. When I reduce the dimension to degrees like 10, the rate of recognition reduces to 70-75%, and we see that non-negative ICA works better than PCA here, although ICA is a little bit short here. But for the lower dimensions, we see that non-negative ICA, both non-negative ICA and ICA, they perform better than PCA in the dimension of 20. But as the dimension goes, of course the algorithm gets slower and slower, and the PCA gets better than them. But in low dimensions, non-negative ICA captures some features that PCA cannot. And if we see the error rates for different dimensions, we see that the green line, non-negative ICA, is in the short, in the small dimensions, is always below the red and blue line, which is Eigen-Faces and classical ICA. Non-negative ICA is way better than classical ICA in low dimensions, and in longer dimension, higher dimensions, they are the same, almost the same. And in the lower dimensions, both ICA and non-negative ICA outperforms Eigen-Faces. In dimension of 20, we see PCA is worse than ICA. Here are some examples that non-negative ICA outperformed PCA. We see that for PCA, these two guys are the same person, but non-negative ICA captures some property that uncorrelated PCA cannot. Same way, these two guys are the same person for PCA, but not ICA. To conclude, for enough dimension reduction values, both classical ICA and non-negative ICA outperforms Eigen-Faces. The reason for that is Eigen-Faces uses PCA and it only finds features orthogonal to each other. It doesn't take characteristic features of a face hidden in a higher order statistics into account. Using ICA, some other different features of one's face pertinent to independence is exposed, and they are taken into account too. The improvement brought by non-negative ICA rather than classical ICA is that it reduces the search criteria into space of only non-negative sources, and thus it prevents the miscalculations that can occur in classical ICA due to sign ambiguity. Thank you for listening.